We'll start. Just make sure you capture a little bit of that. Alright, so let's get started. We are going to continue our discussion from last time. But it's Wednesday, so let's start with the parable. This is part 2 of what I said last time. So this is the lion and the rabbit. So this time around there is a lion who's sitting outside a cave, okay, and in a jungle, and then there is a fox that comes along, and then the fox looks unhappy. So then the lion asks the fox, "Why are you looking gloomy?" And then the fox says, "I had this really nice wristwatch and I put it through a washing machine and it's damaged." And then the lion says, "Why don't I fix it for you?" And then the fox says, "How is that possible? You have big claws and this is really fine instrument. It has very tiny parts. I don't think you can fix it." The lion says, "Let me try." And then he takes the watch inside the cave. Few minutes later comes out and the watch is fixed. Okay. Then short while later a wolf comes along, also unhappy. And then the lion says, "What happened?" And the wolf says, "I was working on this paper, my laptop crashed and my disk is dead." So then the lion says, "Why don't I fix your laptop for you?" And then the same thing happens, and the wolf says, "How is that possible? This is a really nice laptop, it has small parts, I don't think your claws are going to let you fix it." Lion says, "Let me try." Goes in with the laptop, and then after some time comes out and the laptop is fixed. And then the lion goes back into the cave, and there's a group of rabbits sitting there with all sorts of fine instruments. Okay, so here the lion is the advisor like last time, and the rabbits are the students. And the moral of the story is, it doesn't matter whether you know how to program or write theorems. What matters if your grad students can. All right, so that's the second part and the conclusion of the story. So we will go back and talk about distributed scheduling. We had one slide left over from last time. And if you remember, I stopped with volunteer computing. I was talking about SETI at home and Berkeley Open Network Computing, all of which allow you to have a group of machines donated by volunteers. There's a centralized scheduler that has lots of small jobs. Whenever the machines become idle, they contact the server sends them some data processing task, they process data. And this has been used in a variety of different contexts. So that's one example of how distributed scheduling is used today in practical systems. Okay, and there's another example, and that is the Condor system and its many counterparts. There are a bunch of these systems that do roughly the same things. Okay, so Condor essentially is a system that tries to utilize idle cycles on a workstation in a lab. Okay? Unlike volunteer computing, okay, Condor is a system that system administrators deploy on desktops or workstations in an environment. Whenever users are not using their desktops, maybe they go home in the night and the machine is just sitting on their desk, the machine can then run long batch jobs or simulations. So essentially, you're harvesting idle cycles that are all, on machines that are already in your environment. Okay? Condor was a system that was designed in the 90s, if I remember, right? To do exactly that. So it requires you to have a small piece of software that runs on each machine. There are Condor servers. Users can submit jobs to Condor servers. The server essentially has a batch scheduler, and jobs that have been submitted by any user is queued up. Whenever machines become idle, these jobs are then sent to those machines. Okay, and the machines compute, do computations, and then send back results. Okay. Condor also implemented, okay, as part of its system, many innovations that we have seen in the context of Sprite and V and all of the distributed scheduling techniques, which include suspending a job, migrating it from one machine to another. It has process migration. Process migration, of course, requires that your machines in your Condor system be homogeneous. You can't migrate a process from a Windows machine to Linux machine. That doesn't make sense. Okay? So if you have a heterogeneous environment, some of those features are not available, but those machines can still run bad jobs, okay, of various sorts. But if you have a homogeneous environment, you can do a variety of things. You can have flexible job scheduling policies. You can have more than one queue. You can assign priorities to queue and so on. Okay? So that's an example of distributed scheduling as it exists. So there are many universities, and so this was developed at the University of Wisconsin. It still is an active project today. They keep releasing new versions of it and so on. Okay, so that's something that exists today. There are many other similar systems. Okay, one is called Sun Grid Engine. There's another one called DQS, Distributed Queuing System, and so on. So Sun Grid Engine is actually used here at UMass. There's a cluster that we have that has lots of servers. Okay? And then users can submit jobs to the cluster. So if you are a research student working on a research project, you can get an account on the cluster. Again, so there are many others who also have accounts. And then if you want to submit a job to do some computation, it could be a MATLAB or R or any data processing job or a compute task, you can submit it to a queue. Okay? And then this SunGrid engine essentially is a batch scheduler. It has a queue of jobs that have been submitted. Anytime servers in your cluster become idle, it will take the next job in the queue and send it off. Okay? So essentially this is also equivalent to the processor pool model that I alluded to in the very first class. So you have a queue of jobs. Okay, so then you have a set of servers. Okay, so this is your cluster. That's a job queue. And then there's a scheduler here. So anytime any of these become idle, you just take the next one and then you just send it off to the servers. And they will compute, and then when the job is done, this repeats. And because this is a large cluster and there are lots of users, there will always be some job waiting, for example. If there is not, then the servers will idle. But if there's a queue of jobs, you'll just use all the machines in your cluster. Okay? So that's another example of a scheduler that will perform distributed scheduling for us. Okay, so this is something that if you have access to a cluster called Swarm, which is a cluster that we have in this department, you will see that SunGrid engine is actually a distributed scheduler that runs on it. Okay? Just some example case studies and scenarios where these kinds of ideas are used today. Any questions here? I'm going to switch gears and change topic. Okay, so we've done scheduling. Okay, we went from uniprocessor scheduling, we looked at multiprocessor scheduling, we did distributed scheduling. Okay, we looked at processes and threads and all of that in that context. Okay, we are done with that. What I'm going to talk about today is a topic that's still related to this broad topic of processes and threads and whatnot. Okay, and that's virtualization. Okay, so I'm going to describe to you or define what is virtualization. You've probably heard of this term. If not, you've used virtualization technologies in various shapes or form. So we'll look at it in a lot more detail, try to understand what it is, how it works, what kinds of advantages it provides, and so on. Okay? So let's start with the definition of what is virtualization and just a little bit of history, okay, why this actually came about and what. Okay? So the very broad definition is here. Okay? It's essentially a way for a machine that has a certain interface A to mimic a separate interface B. Okay? And that's an example that's shown here. Okay? So this is, let's say, a standard machine that has an interface A that it exposes. So that could be an OS interface. It could be any interface. We'll talk about what this is. And there are programs that are running on it. Okay, here is an example of virtualization where you have a machine that actually has an interface, native interface B, and there's a software layer that actually implements interface A using interface B and exposes interface A to higher level programs. Okay, in this case, a machine that has interface B is mimicking interface A, and this is what we will call virtualization. Okay, you are virtualizing interface A using interface B. Now let's try to make that a little more concrete. That's a very abstract definition. You're just implementing one interface using another. So we'll ask why this is important, or where does this make sense, and how it arose. Okay, so although it is a technology that has become popular recently in the past decade or so, is by no means a new technology. It was developed in the 1970s. Okay? So it's fairly old, it's more than 50 years old at this point. It was introduced by IBM in the 70s, and it was introduced for their mainframe computers. Okay? And here is the reason why they actually decided to implement virtualization. So in those days, hardware cost a lot of money. A mainframe computer, it cost millions of dollars. Even today it does, but in those days, $1 million was worth more than it's worth today. Okay? So let's say you're a company or an organization that spent a lot of money invested in a mainframe machines, and then you have developed applications that run on your mainframe that runs all sorts of that performs all sorts of tasks for your organization. Maybe it does payroll, it does accounting, and all of those things. Okay? Now, maybe a few years later, machine becomes old. Okay? It's time to then upgrade your machine or buy a new one. Okay? So you go back to your vendor, let's say in this case it's IBM, and say you want to buy a new mainframe. And then IBM will say, well, we have a latest generation of mainframe, is much faster, is much better. Okay? It has all sorts of new hardware innovations, okay, and so on. And it will cost maybe again another $1 million or so dollars. And by the way, we have introduced a new architecture, a new CPU that's much faster, and it has a much better interface. Okay, so maybe that makes you as an organization happy. But then if they say because it has all sorts of new features, we changed the OS, now all the interfaces have changed. So none of your old applications are going to run as is anymore. Okay? So that, if you are a customer, doesn't make you happy, because you can go buy a new machine, but if none of your old applications that you spend a lot of money to develop work anymore, they have to be rewritten or ported, that's going to be a lot of work. Okay? So that's not a good way to sell hardware. Okay? Because then you're saying buy $1 million, but then get a lot of programmers to take all of your old code, modify it, port it, and get it to run on the new machine. Okay? A lot more work than just buying a new machine. But on the other hand, if they say all of what they said, saying you have great machine, much faster, better architecture, and they say, by the way, if you have applications that were running on your old machine, they will run as is, even though everything has changed. We'll give you a piece of software that will just let your applications run as is without any change whatsoever. You don't have to change anything. Just take the binary, it will run, even though the underneath everything is different. Right? Now that makes you as an organization much happier, saying, okay, I'll invest all of this money, I can develop new applications with all of those new features, but if I have old ones, they continue to run, and that's great. So you don't have to do anything to port them and whatnot. Okay? So in order to actually make that kind of an argument, they essentially had to develop virtualization technology, because the hardware kept evolving very quickly. Even today it does. But then if you change the processor family, because you say, here's a better way to build processors or CPUs, or here are all these new features that you introduce in your hardware, you change the OS, you introduce new features and new system calls, things break, the old programs don't work anymore. Okay? Now in order for portability reasons, to let your users continue to run old programs, what you have to do is you have to build a software layer, okay, that runs on your new machine. Okay, it mimics the old machine. That's your old interface A. Okay? So the programs that run using this layer, to them it looks like they're still running on an old machine with the same interface A that was on the previous generation machine. This is your old machine that exposes interface A. Okay? So here some programs are going to use the virtualization layer and run unmodified. Of course, you can develop new program that directly uses interface B, takes all the advantage of what the new hardware has to provide. Okay? So that is essentially the genesis of how virtualization came about. They designed this technique that allowed their customer base to continue to run all sorts of old programs unmodified, okay, using virtualization technology. Okay? That was in the 70s. Okay? Now there are new reasons why we use virtualization today, but that's how it came about. Yes, question.
So would like a part of the libraries and an API be considered a form of virtualization? I mean, intuitively that seems wrong. But.
Yeah. So question is the portable library going to be a form of virtualization? If it is emulating a different interface, it will be, and I'll talk about different forms of virtualization. What you're talking about is actually application level virtualization. Okay? So there are libraries that will virtualize at the application level. They do precisely that. Okay? So this is a very broad definition. Okay? When you have maybe used virtual machines and whatnot, there is a certain kind of virtualization you have used, but that's not all the kinds of virtualization that exist. Okay? Even application level virtualization will actually be considered a form of virtualization. And we'll talk about that in just a minute. Okay, so here is essentially a picture that shows you what interface you are actually emulating. I just said interface, that was a very general definition. Okay, now there are different forms of virtualization. They mimic different kinds of interfaces, and that will give you different kinds of virtualization. And here are 4 different ones. Okay? So at the very bottom you have hardware. Okay? So if you're running on one hardware, one CPU, and you're mimicking another CPU or another kind of machine, that's called hardware level virtualization. Okay? So essentially you are mimicking a processor, okay, and maybe all the other components on the machine connected to the processor. Okay? This allows you to mimic one processor family using another. And we'll talk about that in a moment. Okay? So that's hardware level. Okay? If you are at this level, okay, this is the next level of interface. If you are using one OS interface, which is essentially the system call interface, okay, to mimic another interface, okay, that is called OS level virtualization. In this case, you might have one form of one OS mimicking another OS or another system call interface. It could be an old version of the same OS, doesn't matter. Essentially, you are mimicking at the system call interface. Okay, that's OS level virtualization. Okay, you can have the next level, which is the library. That was the question that was asked here. So you can have application level virtualization where you use a library interface to mimic another library interface. Okay, that's application level virtualization. Okay, Java is actually a form of virtualization as well. Okay, that's why you have a Java virtual machine. Okay, so that's JVM. It's a form of virtualization. Typically, that's your basically there are multiple things happening in Java, but essentially you get a Java interface. So that's all being done at the application level. Okay, so for us, when you look at virtualization, we'll have a broad definition, and there'll be different kinds. Okay? If you have actually used virtual machines, VirtualBox or VMware or Zen and whatnot, a lot of that is actually at this level. Okay, you are actually at the hardware level. Okay, but we'll see that there are other kinds as well, and we'll talk about them. Okay. Any questions? Is it clear what virtualization means? Yes. Okay. So depending on what is actually mimicked, at what level are you mimicking one interface using the other, you are going to get these kinds of different kinds of virtualization. So we are going to start at the bottom. Okay, today I'm going to spend most of our time talking about OS level virtualization. I'll give a glimpse of the other kinds. Okay, and next time I'm going to talk about OS level because that has become popular as well. Okay, if you've used things like Docker or heard of Docker, that's actually doing OS level virtualization. It's a different kind altogether. Okay, so I'm going to add some more material to the class, and we'll talk about OS level next time. Today we'll start with hardware level. Okay, so let's start with a little more details of different types. I talked about them briefly, but here is a little more detail. Okay, so now there are different techniques to actually implement this virtualization as well. Okay, so the first of the most basic one is called full emulation. Okay, in this case, okay, the software layer, which we'll call a virtual machine or a virtualization layer, emulates complete hardware. Okay? So this is a software emulation of, let's say, a PC. Okay? Every component that you actually have on a PC, that's a processor and memory and a disk, is actually emulated in software. Okay? So when a process runs or application runs on such an emulated software, it looks like it's running on a real PC. Okay? It's just that the actual PC doesn't exist. It's completely emulated in software using the machine resources underneath. Okay, so it just looks like it's a slower PC because it's running a software emulation. Okay, so you can run unmodified operating systems on top of an emulated layer. Okay, you can take a full Windows or Linux or OS X or any operating system that you can think of, so long as your emulation layer implements the hardware that the OS is designed for. Okay, it will run unmodified. So if your emulation layer emulates an x86 Intel PC, anything that runs on an Intel PC will run on that software. Okay? Just that it will run slower because you're emulating all of the components. Okay? There are many examples of this. There's something called Box. Okay? I don't know if anyone has heard of this. Yeah, it's an open source software that implements emulation for a variety of different processors. Okay? you can emulate embedded processors, you can emulate x86 processors. So it's a growing family of processors that Box can emulate. It can emulate different kinds of machine, okay, all in software. Okay. There's virtual PC for the Mac. Okay. So this was back in the days, maybe 5-6 years ago. Apple switched all of their machines to x86 processors. Before that, a Mac would run on a PowerPC processor, different processor family, RISC processor. Okay? So clearly, if you are running on a RISC processor, if you take an x86 application, it's not going to run a different assembly instruction, different families of processor. Okay? So in those days, you could buy a software which Microsoft made called Virtual PC. Okay? Virtual PC essentially emulated an entire x86 PC. It would run on a Mac, which was a PowerPC based processor. It would emulate an x86 PC. Okay? This would then allow you to run Windows on top of a Mac. Okay? And then you could run your Windows applications, Office applications, and whatnot, even though your machine was actually not even the same processor family, different hardware altogether. Okay? So that was a commercial product. There's something called QEMU, which is very closely related to Box, that also does the same thing. It does emulation. Okay? So that's the most basic form of virtualization, is full emulation. Okay? In this case, you can take any hardware family, okay, and then emulate any other hardware family using that virtualization interface. Okay? Typically, you try to emulate some other family and run programs that were designed to run on that other hardware on this system. Okay? That's one. The next one, okay, is called full or native virtualization. Okay? So in this case, you are emulating the same interface, okay, using a native interface. Okay, so what that means is, if you go back 2 slides, you're using interface B to also emulate interface B. In other words, A and B are the same interfaces. Okay, so emulating the same interface using the native interface. Okay. In emulation, A and B are completely different interfaces. You could have, let's say, PowerPC processor, you're emulating x86 processor. Okay. So in full or native virtualization, the A and B are exactly the same families. Okay. So you're emulating x86 using x86, for example. Okay. So now you can ask, why would anyone do it? Okay. Why are you trying to emulate the same interface when that interface already exists on the native machine? Sorry, what did you say? Okay, upgrade. What are we upgrading?
Any instruction sets we are upgrading, which will not be that compatible.
Okay, so okay, you could do that, although we are actually not changing anything at all. We're doing exactly the same emulation. If you have changed the hardware, then you are actually back in emulation world where you are emulating old hardware or something like that. Yes.
We are like experimenting with some application. We don't want that to like ruin the actual operating system.
Okay.
We would experiment on application.
Yeah, you had something.
If you want to change some system parameters like the memory.
Okay. So 2 suggestions here are, if you want to do testing, okay, you want to test something, you don't want to muck around with your native machine, you can run it on virtualization layer, and then you can discard it later. And then the other thing was, you can actually play with different configuration parameters. So all of these are actually examples. Of course, you can even run a different operating system. Just because the hardware interface is the same doesn't mean that the software that runs on the virtualization layer is the same. So if you have a Linux machine, you have this virtualization layer that gives you another x86. You can have software PC, you can run Windows. Okay? Or if you have Mac, you can run Windows on Mac or some other operating system on the same machine. Okay? This is often used in for development. Software development is a good use case for this. There are lots of virtual machines that give you software implementations of a PC. You can basically have your entire test environment isolated from the rest of your system and just run tests inside your system, or do builds inside the system, and so on and so forth. Okay? So if you use VMware, VirtualBox, Parallels, any of these software, they are essentially doing full or native virtualization. Okay? Most of them actually run on x86, so you're emulating a software PC using an actual PC underneath. Okay? And who has used VMware virtual machines or Box or so quite a few of them. So you used native virtualization. We are going to talk about how that works underneath. Okay, well, how does it actually make it work? Okay. Now the thing I should mention is native virtualization is going to be more efficient than emulation because here the emulated processor and the actual processor are the same. Okay? So if your program is going to execute an assembly instruction, let's say add, that's the same instruction that the native CPU supports already. So you can just execute the same CPU instruction. Okay? In emulation, if the if the program is going to say add, you have to decide how to implement the add assembly instruction on this emulated processor using whatever assembly instruction exists underneath. There may be some variant of add that the native processor supports. You have to do translation. Okay, so this is like, think of language translation. You speak a sentence, then out comes a sentence in some other language. Here, you don't have to do any translation. The instructions are the same. So you just run them as is. So this is going to be much faster, okay, more efficient than emulation as a result. Okay, because the emulated part is just other aspects, not that the processor instructions need any translation. Okay, is that clear? Okay. So then the next technique we'll talk about is called para-virtualization. Okay. So in the previous two cases, whether you have emulation or you have full native virtualization, you are able to run an entire operating system on that emulated virtual machine or a full native virtualization based VM unmodified. You can essentially take Windows or Linux or Mac OS X or whatever OS you want and run it unmodified on the VM. You don't have to change it at all. Okay? And then the virtualization takes care of the rest. In para-virtualization, it's a form of virtualization, but it requires some modifications to the operating system kernel to make it aware of the presence of the virtualization there. In the previous two cases, the OS or applications that run on the OS don't even know that they are running on an emulated machine, not a real machine or a virtual machine. Okay? In this case, you are actually modifying the OS to let it know that it's running on a virtual machine. Okay? And hence, you can do certain things you could not have done in other cases. And I'll talk about what those things are in a little bit. Okay? Examples of para-virtualized systems are Zen. Okay, that's a open source virtualization software that you get on Linux. Okay, there's VMware has a thing called ESX server that used para-virtualization. Okay, I'll talk about that as well. Okay. The next level of virtual, these are of the first three are all hardware level virtualization. We're emulating hardware. Okay, so now we are going to go one level up to the next level in the stack. So if you remember, so I talked about three ways to do this. Okay, emulation, full virtualization, para-virtualization. Now I'm going to talk about OS level virtualization. Okay. So in OS level virtualization, essentially you have one OS emulate the interface of another OS. Okay. The most common scenario is the OS is emulating a previous version of the kernel. Okay. Let's say a new version of a kernel comes up. Okay. Sometimes they introduce new system calls or change the parameters of a system call and so on. This is going to cause applications that were developed on a previous version of the kernel to break. Okay. Now, if you actually have the OS has the ability to emulate the previous version of the kernel, it's emulating the previous generation of the kernel, then your old applications can run unmodified. Okay. That's one scenario where you can use OS level virtualization. Okay. Solaris is a good example where they did this. Solaris has a technology in it called containers. Okay. And then, so if you are running Solaris version 10, okay, you can create a container and say emulate kernel version 9.1.3. Right? And then if you run an application on that container, to that application, it look like the kernel version is running on is an older kernel version, even though the actual version is newer. Right? So nothing is going to break for that application, even though the native kernel now uses maybe a newer version of system call interfaces and whatnot. Okay? So that's one scenario where it's used. In the Linux and BSD world, there are technologies called BSD jails. Linux has vServers and LXC now, okay, Linux containers. All of them actually implement OS level virtualization. So if you use the Docker that's using OS level virtualization. You essentially get an OS container, okay? And that essentially isolates the application from other applications on the machine. So I'm going to show you a picture here. Okay. So let's say that's your OS. Okay. So here are applications that are running. Okay. A, B, C, and so on. Okay. The normal case, when there is no virtualization at all of these applications run and they compete for resources. They might compete for memory, they might compete for CPU and so on. And the OS schedulers take care of allocating resources in the best possible way to the applications. Okay? But if some application starts misbehaving, okay, it just starts running lots of computation, and it's going to come at the expense of the CPU time some other application is going to get. Okay? So in a normal case, when there is no virtualization, there is no isolation between applications. One application can impact the performance of another application. Okay? On your machine, if you have one process that hangs, it slows down everything else. Okay? That's no isolation between application or processes. Okay? Now, if you use OS level virtualization, what you can do is, in addition to emulating an interface, you can also allocate a certain amount of resources to a process. You can say this process, okay, which is running on this OS level virtualization technique, we'll call this a lightweight VM, should get 500 megabytes of RAM. Okay? It should get 20% of the CPU and no more. Okay? You can specify these resource limits to your OS level virtual machine. Okay? That will then prevent this process from getting anything more than whatever has been allocated to it. That's number one. Number two, when it runs inside this container, it doesn't even see what's outside. Okay? So B is no longer able to see A and C at this point. Okay? You can even isolate the file system on your disk, saying this process has only access to certain directories, okay, and no others. Okay? So you cannot even go and change directories and look at other data on your system. So it basically provides you a form of resource isolation. Okay? This is what containers technology will allow you to do. Okay? So that is OS level. We'll come back to OS level virtualization next time and talk about how it works. Yes, question.
Is it possible for A and C to influence B though, or
Okay. Is it possible for A and C to influence B? Not quite, because the OS is then going to essentially partition off its resources and give it so much. Okay? A and C get the rest. A and C could be running normally on the OS as it does, or they could be in their own containers. Okay? You can have more than one container here on these machines. Yes.
The same thing can be done in hardware level virtualization also.
Okay. Is just kind of the same thing be done in hardware level virtualization? In hardware level virtualization, you are going to get this out of the box, because what happens in this case is essentially you have virtual machine A, you have virtual machine B. Okay? Virtual machine A runs an OS A, this runs an OS B, and then is going to run some apps. Okay? This is also going to run some apps. Okay? That's the picture for hardware level virtualization. Your entire, essentially a machine, which is your CPU, RAM, has gotten partitioned across virtual machine. When you create the virtual machine, you are going to provide the same level of requirement, saying this VM gets 2 GB of RAM. Okay? Allocate it a single core. If you have multi-core, you can have 2 cores, because one core is given here, one core is given there. That then you've taken your cores on your machine and split it across your virtual machines. Okay? So now VMA can only get what's been allocated to it. Okay? So it goes without saying that for hardware level virtualization, the performance isolation is even stricter. Okay? Because in this case, if B triggers a bug that crashes your kernel, A and C will crash with it, because they are all running on the same kernel. They share an OS kernel. Okay? Here the isolation is even stricter, because if A goes and crashes its kernel, the other virtual machine executes as is. It doesn't matter. Okay, so it's a much stricter isolation than what you get in OS level. Okay, so that's OS level virtualization. Come back to this next time. And then the last one is application level. So here you are emulating a library interface. Okay? The simplest example of this is the Java virtual machine, JVM. Okay? Anytime you run Java, it runs on an abstract machine called a Java virtual machine. that essentially emulates an interface and it uses libraries. Okay, so JVM is an application itself. Okay. There are two other examples. If you used Wine, okay. Has anybody used Wine? Okay. Several of you have used Wine. So that is a library emulation of the Win32 interface. Okay. What Wine does is that it allows you to run Windows applications on some other machine. Okay. The way you do it is Wine is a library that essentially re-implements the Win32 Windows libraries. Okay. So Windows has native Win32 libraries. Okay. So if you have Windows application, it uses Win32 or Win64 as the newer version. It basically uses those libraries to run. Okay. So if you want to run a Windows application, a Windows binary unmodified on another machine, you minimally need the Win32 or Win64 libraries on this other machine. What Wine has done is an open source software that has essentially re-implemented the Win32 libraries. Okay? So you just take those libraries, so you can re-implement it on Linux or some other machine like Mac. So you can essentially run Windows applications just using the right libraries. You don't need to actually have Windows running. Okay? You just need the right libraries to run. Okay, that's all you need. So that's an example of OS level virtualization. Okay, so this is one library implementing another one. That goes back to the question you had asked. Right? And then there is another one which you may have not have heard of. That's called Rosetta. Okay, that is a technology that was available on Macs. It's now been discontinued. Okay? So what Rosetta did was something like what Wine did. Okay? But when Apple switched from PowerPC to Intel, okay, lots of people had spent a lot of money buying applications for their Mac, okay, PowerPC Macs. Okay. Now Apple says the same thing, the argument that IBM made, saying here is a faster Mac. Okay. By the way, we switched to Intel, so none of your applications are going to work. Go buy a new version of Office and spend a lot of money rebuying all the new applications again. That does not make you happy as a user, saying I've spent so much money buying these applications, now to throw it away, I can't migrate it, I can't run it because everything has changed. New hardware, different processor. Okay? So what they did was the exact thing that IBM did maybe 50 years ago. They came up with this library called Rosetta that was transparently installed on all newer Macs. Okay? So if you just took a PowerPC binary, okay, and simply double clicked on it, it would just run. It wouldn't even do anything because the OS would automatically figure out this is not an x86 binary. It's a PowerPC binary. It would start up the Rosetta library, which was simply emulating x86 instructions and old interfaces, and it would let your application run as is. Okay? So you could run essentially Mac applications are designed for a completely different hardware transparently on your newer Mac. So all your applications essentially ran unmodified as is. They may run a tad slower, but at least they run, so you can continue to use your application. Okay, so there's another application level virtualization. Okay. It also did emulation because it not only had to emulate the old OS interface, but it also had to dynamically emulate assembly instruction because PowerPC used a different instruction set altogether. Okay. So in Wine, you're running x86 Windows applications on an x86 machine. You're not translating assembly instruction. Here you are doing lots of other things in the back. Your question.
Is there any sort of progression of like performance penalties on these, or is it basically implementation specific?
Okay, is there a performance? That's a good question. Is there a performance penalty? There indeed is. As you go lower down, you are going to get more benefits like resource isolation, performance isolation, but the overheads are high. At the very bottom, at hardware level virtualization, you have to run an entire OS in order to make use of that virtual machine. Okay? You can't even share OSs across virtual machine. Okay? As you go higher and higher up, there's less and less sort of overhead in the virtualization software. So the application level is the most efficient, okay, in terms of performance. It is the least, I shouldn't say efficient, but it has the least amount of isolation. Okay? You have basically interference between other things that are running on the machine. Okay? So more isolation at the bottom, better performance at the top. Any questions here? Okay. All right. So I think most of you said you've seen virtual machines. Just going to show you for those of you who have not. Okay, this is VirtualBox. Just a piece of software. It is emulating an x86 PC, complete emulation of an x86 PC. So I have actually a virtual machine in there. I'm just going to start it up. Okay, so this is essentially a Linux virtual machine, or virtual machine that's running Linux. So you'll see that. Let me just cut all that out. So you'll see essentially this is running Ubuntu, okay, on my Mac, because Ubuntu is essentially running in a VM. The VM is emulating an x86 PC. Okay, so Ubuntu, it just looks like it's running on a real PC, okay, except that it's running on a software emulated PC. Okay. You can create, and this is just, we don't have to go into this, but essentially this is running a full-fledged Linux environment on my Mac. Okay. You can have multiple VMs running at the same time. Each is going to get its own emulated PC. Each is going to run its own OS. Okay, there could be different OS. I could run Windows on one and Linux on the other, or whatever I want to do. Okay, so that's an example of hardware level virtualization. And in fact, we'll see how this works in a couple of slides. Okay, but if you have not used it, it should give you some flavor of how virtual machines work. They essentially allow, so you can create new virtual machines as well. Okay, so if you just say go machine, you can then, you have to go to settings to do that. So you can create a new blank virtual machine by going here. Okay, and then it will be a machine that has nothing in it. You can install a new OS, for example. Okay, so do things like this. Okay, so you can, like you'd shut off the PC, you can do all of that as well. Okay, so you can then go and pause it or do whatever you want. So I paused the PC. So the virtual machine is just suspended currently. Okay, you can power it down, you can restart it. All the things you can do on a real machine, you can do here. Okay, so that's just a quick glimpse of what hardware level virtualization does. We're going to talk about them in a lot more detail next. Any questions here before we move on different kinds of virtualization technologies? Yes.
What the difference for the OS scheduling for different types of virtualization?
You're saying what does the OS scheduler do for?
Like for the OS level virtualization, so
Yeah.
different virtual machines will have different OS. So the guest OS will do the scheduling, or the host OS will do the scheduling.
Okay, so you are asking different questions. So
Yeah.
you're saying if you have multiple OSs here, who's doing the scheduling, right? So inside this virtual machine, there will be applications running. Okay? This OS is going to schedule them, okay? Because that's all you're going to do. Okay? Inside this virtual machine is another operating system. Okay? There will be processes running there. This OS is going to schedule them. Okay? Now we'll see there are many kinds of virtualization. There is one where you have what is called a host OS here. Okay, that's what I just showed you. There was Mac running, and then there was a VM, and there was a Linux running inside Mac. So this one is basically going to just do it. This entire thing is going to look like a process, like any other process. Okay? Even though it's a virtual machine, it's a software emulation. It's a program that's emulating a PC. It's a process. So it will just schedule this process as if it's any other process on your system. Okay? And these processes will coexist with something else. You can have your Chrome browser running here. Chrome browser and this virtual machine will just look like two processes on your system. Right? So your guest OS and host OS are going to schedule like they always did, but they are scheduling whatever they can see as native processes. Okay?
Yeah, but for the application level virtualization, there is no guest OS. So the library will do the translation, or?
Yeah, so if you have application level virtualization,
Yeah.
the translation is done in the library. The library is the one doing the emulation. Okay? There's no scheduling there. You're simply, whenever you run, you're just going to do the translation. Yes.
Yeah, so the main principle of virtualization is isolation.
Is the main principle isolation? Of the main principle is to mimic one interface with another. You are trying to pretend like you are some other environment using a native environment. As part of that, you will have to provide resource guarantees, you will have to do scheduling and all these other things. Okay. All right. So now, with that, we are going to go and look at hardware level virtualization in a little more detail. Okay. So here are two examples of, there's one more on the next slide, two examples of hardware level virtualization. Okay? So this virtualization layer now is going to be called a hypervisor. Okay? It's also called a virtual machine monitor or a VMM. Okay? That's what is actually going to run on your hardware. Okay? And there are two kinds here. Okay? This one, which is called a type 1 hypervisor, is also called a bare metal hypervisor. The type 1 hypervisor is the thing that actually runs when you boot up. Okay? There's no OS in this case. The hypervisor is the OS. It's just going to boot up and then it's going to create some virtual machine and then you can boot each virtual machine independently. Okay? This is called type 1. This runs more in the server environments. Okay? This is called type 2 hypervisor, where you have a host operating system that you're going to run on your machine. And then your entire hypervisor and the virtual machines are going to run on top of that host operating system. Okay? That is what I showed you here. Okay? The example that I just gave you, and if you actually run VMware or VirtualBox or whatever on your desktop, you essentially use type 2 virtualization or type 2 hypervisors. Okay, type 2, there is a host operating system that's going to actually run on your machine. The hypervisor runs as a process on your host operating system. It creates virtual machines, so a guest operating system can then run inside the VM. So there are two OSs there. Okay? There's a host operating system, and for each virtual machine, there's a guest operating system. Here, there is no operating system at all. The hypervisor is actually running. So when you boot up your machine, the hypervisor boots up. It has a tiny kernel that does whatever an OS would do. Okay? So these are the two kinds of hardware level virtualization. So type 1 is runs on bare metal, type 2 hypervisors run on host OS. Okay? So and there's a guest OS that runs on top of the hypervisor. In both cases, the hypervisor is emulating a full-fledged machine. Okay? Or it's with native virtualization, it's essentially emulating an entire machine in PC, in software, an entire PC in software in most cases. Yes.
I mean, what emulation exactly is happening in type 1? Because it just seems like a laptop on dual boot or something.
So what is the emulation happening? So this is not dual boot because all of these OSs are running at the same time.
Okay.
It's not like you booted Windows or Linux. You have one virtual machine on your, so let's say this is a 16 core server. Okay? If your application doesn't need 16 core, you can construct smaller virtual servers. So you can say this virtual server has 2 cores out of 16. This has 2 cores, and then this looks like its own machine you boot Windows. So they're all running at the same time. And that's the main difference. Yes?
The type 2, can the guest OS take all the cores?
Can the guest OS take all the cores? They can take all the cores. It depends on when you created the VM, you have to allocate resources to it.
So the
And you
ready queue of the host OS knows about the processes of the guest OS also?
So the host operating system will not actually know anything that's going on here. It will only see a process that's the hypervisor. It doesn't actually see those processes. It doesn't see the operating system. It just looks like it sees one process, that's the virtualization process. Everything that's happening inside is hidden to it. It doesn't see them at all.
So is it a uniprocessor kind of thing, the guest OS can take?
Is the guest OS uniprocessor? So it doesn't have to be. If you have 4 cores on your machine, you can give it 2 cores. You can even give it all 4 cores, but you can't dedicate the 4 cores because there are other things. You can say take all 4 cores, share it with other processes. So that is flexible. Okay. Yes.
We talked about the 3 kinds of hardware virtualization earlier. So now that this maybe to this
So this is only hardware level. I'm just showing you now different ways of doing hardware level virtualization. Okay. So OS level and application level is a separate discussion. So I described all of these things, right? So this is one way to do hardware level. This is another way to do hardware level. Okay, this is the third way to do hardware level. This is OS level. This is application level. Okay. Now what we are talking about is more details of this. This is by far the most common way of doing hardware level, native virtualization. So type 1 and type 2 hypervisors are essentially doing native virtualization. They're just 2 different ways of doing native virtualization. Okay. All right. So here, this is type 1 hypervisor, that's type 2 hypervisor. I'm going to come back to that in just a minute. We are going to see how they work. Okay, so essentially we'll now look at a little more details of how to implement a hypervisor, or what are some very basic things you need to do in order to implement virtualization technology. Okay, how is all this emulation or native virtualization working? Okay, so for this you need a little more hardware knowledge, and I'm going to draw a picture here. Okay, so again, this goes back to some background that maybe you encountered when you did an undergrad class in OS. If not, this is a quick refresher. So let's take a typical CPU. Okay. Now, most processors, okay, will at least support what are called two modes of operation, a user mode and a kernel mode. Okay. Now, if you have a process that's running in user mode, okay, it will be allowed only to execute a subset of the instructions that the processor supports. Okay. Anything that requires you to have trust is not going to be allowed in user mode. You have to be in kernel mode. The CPU has to be in kernel mode in order to execute those instructions. Okay. So a simplest example, okay, there are many such instructions, but let's take simplest one. Let's take the halt instruction. Halt instruction shuts down your machine. Okay, so halt instruction can only be executed in kernel mode. Okay? This is because if you let a user application just call halt, some malicious application is going to call halt and your machine will shut down. Okay? So you don't allow arbitrary user processes to execute certain instructions. The halt is just a pathological case of why you cannot trust applications to do this. On the other hand, okay, if you're in kernel mode, clearly only the kernel runs in kernel mode. Kernel, you can give it, it's a trusted software. If it's halting the machine, there is a reason it's doing it. Maybe the user wants to shut it down. Okay? So you allow anything running in kernel mode to execute whatever you want. But in user mode, you restrict what a process that's executing in that mode can do. Okay? So every processor, hardware processor that you have, okay, will at least support these two modes. Okay? Most families will actually support more than two. Okay? In particular, if you take an Intel processor, i386 or x86 processor, it has more than one mode. It has, and they call them rings in x86 terminology. Ring 0 is the most trusted ring. Okay, so you can do whatever you want in ring 0. And then there is ring 3. It maps onto the user mode. That's the most restrictive. Okay? There's only certain things can be done, and many things are disallowed in ring. If the CPU is in ring 3, okay, which means it's operating in ring 3 mode, only certain things are allowed. And there is ring 1 and ring 2, which place more and more restrictions. This is the least restrictive, that's the most restrictive. Okay? So typically, if you have just a normal OS running, then all user processes run in ring 3, okay? And the kernel runs in ring 0. And now in virtualization, you are going to use the middle rings, because otherwise you don't need them. Okay? But first you need to understand this hardware feature and why it exists. Okay? Essentially, to provide protection and prevent an arbitrary user process from doing some random things and causing harm, you are going to run it in a more restrictive mode, or the processor will support this mode. This is just basic computer architecture. Okay? Any questions on this before I then talk about how virtualization is going to use some of these features? Is that clear? Okay. So now let's talk a little bit about what virtualization technology uses. Okay? If you typically take again a CPU, you will see that there are different kinds of instructions. Okay? There is something called a sensitive instruction. These are essentially instructions that are only allowed in kernel mode. Okay? They are sensitive. Okay, halt is a sensitive instruction. You only allow it in kernel mode. Okay? Changing page tables or memory maps is a sensitive instruction. Okay? You do not let user processes go and change memory settings, because then a user process can get access to some other process's memory, which is disallowed. Okay? You only let the kernel change page table information and so on. So these are all sensitive instructions. Okay? There's another class of instructions called privileged instructions. Privileged instructions are the ones that cause a trap, okay, or an interrupt. If they execute, they will cause a trap. Okay, so Think of these are instructions that result in a trap. Okay, so privileged instructions cause a trap and executed in kernel mode. Okay, so there are many instructions for which you need to generate interrupts and so on, and privileged instructions are the ones that are going to generate an interrupt. Okay. If you can have user instruction trigger trap, like you divide by 0, it's going to cause a trap because that's an error condition. Whenever you have an error condition, that's handled using a trap. Okay. Divide by 0 is just a pathological case. If a network packet arrives, it's going to cause a trap and whatnot. Okay. So there are set of these instructions that are also going to be called privileged instructions. They are going to cause a trap. Okay. Now the main result for us that's most interesting, the reason we have all this background is you can implement type 1 virtualization, okay, on any CPU where the sensitive instructions are a subset of the privileged instructions on that processor family. Okay. That means that if on your CPU every sensitive instruction also causes a trap, then you can implement type 1 virtualization. Otherwise, it's not feasible to implement type 1 virtualization. Okay. Why I'm going to explain in just a moment. Okay. That's just a result, saying if your CPU family is such that all the sensitive instructions you have on your CPU family also cause a trap, okay, are also privileged, then you can go and implement it. Otherwise, it is not possible. Okay, and I'm going to explain why that is the case. Okay? But that's the result that we have to keep in mind. And here is essentially a picture that's going to show you why. Okay, I'm going to redraw that picture here. Okay? With all of this. Okay? So let's say that's your native CPU. Okay? This is your type 1 hypervisor. That's your OS inside a virtual machine, and here's an application. Okay. Now, as I said, when you run any virtual machine, the OS doesn't know that it's running on a virtual machine because it just sees a PC. It's just an emulated PC, but to the OS, it just looks like a normal PC. So the OS thinks that it's running on a normal hardware, and on a normal hardware, OS is in charge. Okay? The OS has full rights to do whatever it wants. It is running on a normal machine. It's going to run in kernel mode. It has full ability to do whatever it wants. Okay, that's what happens in the normal case. Now let's look at the virtualized environment. The virtualized environment, this OS that's running in the VM is not in charge. Okay? It's the hypervisor that is actually in charge. Okay? So in this case, the hypervisor is the one that is actually going to run in ring 0 or in kernel mode. Okay? And the reason for this is there may be more than one. Okay? There may be 2 or 3 OSs. Okay? You can't give them all charge of the machine. They will all trample on one another. So the hypervisor is going to be responsible for resource allocation and everything. It's the one that is the trusted piece of software. It's going to run in ring 0. It's not going to run in kernel mode. Okay? Now, because you have emulated a PC, the OS that's running here thinks that it's also running in ring 0, but it's not. Yeah, because you can't have, say, I trust that, I trust that, I trust this. You can't trust too many people, otherwise things will just go haywire. So you're only going to trust the hypervisor. Okay? It's going to run in ring 0. Okay? Here's an OS. Okay? It doesn't know it's running on an emulated machine. It thinks it's running on physical machine. So it thinks it's actually running in ring 0. Okay? It's going to implement or execute sensitive instructions every once in a while. If the process needs to modify page table, it will try to modify page table. If the process application says halt, it's going to try to execute halt and whatnot. Okay? But you can't give it the ability to do that directly. Okay? Only the hypervisor can do it. So now the question is, if the OS that's running in the VM cannot actually execute sensitive instruction, even though it believes it has all the rights to implement and execute a sensitive instruction, how do we make this work? Okay. Is that clear what the problem is? Okay. In a normal machine, this is not an issue because OS is the one that's running on hardware. It controls everything. Okay. Now the hypervisor is the one that's controlling everything. But this OS, we have emulated a PC, so it believes it's running on a normal PC, so it thinks it has control, but it doesn't. So how do we actually execute are sensitive instructions.
Translate to privilege instructions.
Okay, so this is where this trap thing comes into play. Okay, the OS is going to go and execute, let's say, a sensitive instruction. So let's change some page tables. Okay, but it doesn't have the privileges to do this. But if that sensitive instruction causes a trap, okay, an interrupt, then you are going to switch to kernel mode and the hypervisor is going to start running. Exactly the way in a normal machine, if there is an interrupt, the kernel starts running. Okay? Now here the hypervisor is going to start running. And the hypervisor can execute that instruction on behalf of the OS. OS cannot execute it directly anymore because it's not running in ring 0. Only it's allowed, only some things are only allowed in ring 0. Okay? So that's also shown in the picture here. So whenever the guest operating system executes a sensitive instruction, okay, it's going to cause a trap. That trap will cause the type 1 hypervisor to run. The hypervisor will say, what is the instruction that you want to execute? I'm going to execute it on behalf of the OS. Okay? This is essentially how we are going to make this work. Okay? So the OS will not actually know this has happened. It just thinks it executed as a sensitive instruction, but it was actually executed by the hypervisor for the OS because the OS doesn't have the privileges to do it anymore. Okay? So this is precisely the reason why that result exists. It says this is feasible only when the sensitive instructions also cause traps. Okay? And the reason that's important is in early versions of Intel processor families, if you try to execute sensitive instructions in user mode, you are simply ignored. Okay? This is like a process. If you had an old CPU, you run a process and you implement or execute halt, you put an assembly instruction halt, CPU will just ignore you. It won't do anything. It will just say you don't have the right, it will just ignore you and give it to the next instruction as if nothing has happened. So if that is the case, if these sensitive instructions are ignored, they don't actually cause a trap. Okay. So what that also says is if you have an old processor family from an Intel architecture, they could not implement type 1 virtualization. Okay. The hardware support was not there for you to implement type 1 virtualization. Okay. So you couldn't actually take an old Intel machine and do this. Okay, because it basically your sensitive instructions are essentially ignored. That was the design decision that Intel engineers made for their CPU. Okay. So you couldn't do it. Okay. Then what happened is because there was a need to implement type 1 virtualization, more recent Intel, AMD and whatever else you have that belong to the same x86 families have added specific hardware support in order to enable this. Okay, in order to enable this result. And so you have in Intel, you have to get a processor that has what's called VT support, virtualization technology support. In AMD, you need something called SVM support. Okay, if your CPU actually has that hardware feature, then you can implement type 1 virtualization. And what does this hardware feature do? Essentially, it basically has a bit mask. Okay, where you have one bit for every CPU instruction. Let's say you take the instruction and number them 1 to n. There's instructions of 0 to n. There's instruction 0, instruction 1, and so on. And there are bit masks. Okay? By default, the mask is set to 0. That essentially means if you try to execute that sensitive instruction in user space, ignore. Okay? But you can take any of these instructions and set the mask to 1, which essentially if the mask is set to 1 and that instruction is executed in user space, it will cause a trap. Okay, so you're telling the CPU, if this instruction is executed in user space, please trigger a trap, don't ignore it. Okay? So you can now configure your CPU to say, these instructions I care about. If it's actually executed in some other ring other than ring 0, cause a trap, don't ignore it like a previous CPU would. Okay? And if you do that, then you are essentially going to get that property. If you get that property, you will essentially have that picture. The OS will assume it's in charge. It will continue to do privileged or sensitive operations. They will become privileged operations that trigger a trap. The hypervisor will implement it. Okay? So that's the basis of how type 1 virtualization works. Okay? So your OS is unmodified. Okay? In this case, it's either going to run in user mode or in most cases it runs in ring 1. Okay? This runs in ring 0. This OS is going to run in ring 1. Okay? Applications run in ring 3. Okay? These are the least trusted. This one you run in ring 1 saying you trust this more than the application that's running on it. Okay. So but then the hypervisor is the one that's going to run in the ring 0. Any questions here? All right. So essentially you are going to use this technique to make all of this work. Okay. And I'm going to now talk about type 2 hypervisors. Okay. Type 1 hypervisors needs hardware support. That's the bottom line you should have takeaway. If your CPU does not provide specific support, okay, which means it does not have this property, and many CPUs don't have that property, you cannot implement type 1 hypervisor on that machine. Okay. But if you do, or you have some specific support, then you can do it. Okay, type 2 hypervisor. So this is a little easier. Okay, now the picture has changed. A new picture here. So CPU, guest OS. This is your type 2 hypervisor. So guest OS, that's your applications. This is the picture that you will see, you should have in mind if you are running VMware or VirtualBox on your PC. That's the picture. You boot whatever OS your PC runs, Windows, Linux, Mac, whatever it is. Okay? You start VirtualBox or VMware. That's a type 2 hypervisor at this point, or type 1. Okay? And then on that you are going to boot, you start a virtual machine, you will boot some OS on that virtual machine, which could be different from this OS. I showed you Linux running on Mac. Mac was host OS, Linux was the guest OS, and processes run inside the virtual machine on top of that OS. Okay? So now you can ask, how is this going to work? Okay? So in this case also, this type 2 hypervisor is emulating an entire machine in software. Okay? Guest OS now also believes it's in charge because it doesn't know it's running inside a virtual machine. It thinks it's running on a physical machine. It's going to continue to implement sensitive instructions and cause or call all of the sensitive instructions like before. Okay? And we have to somehow have to make that work. Okay? Now in this case, things are different from type 1. Your host OS is the one in charge. The hypervisor is not in charge. Okay? The host OS, the kernel that you boot on your laptop is going to be in charge. This is simply a piece of application software. This is not even privileged. Okay? It's simply a process or an application like any normal application that's running on the machine. Okay? So then the question is, if the OS goes and calls a sensitive instruction, how is that to be handled? Okay? And the way this is going to work here is we are actually going to do dynamic translation of assembly instructions. Okay? We are going to look, we meaning not we, the type 2 hypervisor is going to actually look at the code that your OS is executing. Okay? It's going to scan the code. Okay? Every time it sees a sensitive instruction appear in the code, it's going to replace that sensitive instruction on the fly with in this case, a VMware procedure. Okay? That sensitive instruction just becomes a function call. Okay? So let's say guest calls halt, sensitive instruction. Okay? As the guest is executing, this type 2 hypervisor is scanning the code, saying what's coming next. It's going to scan the next several instructions. If it sees this, which is say this is sensitive, you will say call VMware halt, and that's a function. Okay? So if you do this, when you actually execute this, this is going to be a function call that actually goes into the hypervisor. In the previous case, you trapped into the hypervisor. Here you are going to go and replace a sensitive instruction with a function call on the fly that will then call the type 2 hypervisor and say the guest OS wants to halt. Okay. Then the type 2 hypervisor will do all the things that as if you had actually called a power down thing. It will save the state or start this terminating processes and just shut down the machine. Okay. Is that clear? So there is no way to do what we did previously, where the sensitive instructions cause a trap and so on. Okay? So what you do is as the guest OS is actually executing code, you're going and replacing code on the fly. This is called dynamic translation. Okay? It's a programming language technique. Okay? So you're going and changing your instructions that your OS actually executes on the fly. Okay? And you're replacing them with procedures that are going to simply call your type 2 hypervisor code, which has then gone and implemented ways to execute or emulate every sensitive instruction. It's clear, it should be clear that for every sensitive instruction, there's a procedure you implemented inside your type 2 hypervisor that emulates the effect of that instruction. Okay? So you're just going to replace it, call that function, and emulate whatever that instruction did. Okay, is that clear? Yes.
So that seems expensive computationally. Would, if you do have the hardware support, could it make you a hypervisor instead?
Yeah. Question is, if you had, so it is going to be expensive because you are going to do on-the-fly translation. Okay, there are lots of techniques that VMware and others have gone and put in place to make this as efficient as possible. Nevertheless, there's going to be overhead. You are actually scanning and changing code on the fly. And your question is, if you had hardware support, would you do it? The reason you cannot do what you did previously is the hypervisor is not in charge. It's the host OS is in charge. Right? In the previous case, this thing was not even there. In type 2 hypervisors, you had CPU, you had the type 1 hypervisor that actually ran in ring 1. Here, this is actually running as a user process. This has no more privileges than Chrome that may be running there. So it cannot even do, even if you trap to it, it cannot do anything more. Okay, it will still have to ask the OS to do something. So this is a better approach to do it. Yes.
Hypervisor runs in ring 3 or any other ring?
So in this case, typically ring 3, but you can make changes as well because this runs as a normal process. Okay? So you don't have any privileges in this case. Okay. So the good part about this is this does not require any hardware support at all. Okay? Because you're no longer actually executing sensitive instructions in other rings. You're replacing the sensitive instruction by function calls that emulate them. Okay? So as a result, you don't need any of the previous properties that said, oh, you needed to have a trap whenever this instruction is executed. Okay? This is why you have been able to run VMware and VirtualBox and all that on all Intel processor families because it did not require any specialized support. Okay, so that's a good part. The bad part is now you are going and scanning code and changing it on the fly and thereby incurring a performance slowdown. Okay? You're going to run far more slowly than you would have run if you had run on type 1 hypervisor, okay, where you are running at full speed. Is that clear? All right. So now I'm going to talk about para-virtualization, which is the third of the technique. Okay? So you can say scanning all this code and replacing those instructions in the kernel is expensive. It's done at runtime all the time, every time you run this. Okay? Another way to do this is actually to say, why not go and change the kernel itself? Okay? If you had access to the source code for the kernel, you can develop a special version of the kernel that's designed to run on a hypervisor, where you go and actually take every sensitive instructions and change it to a function call ahead of time. Okay? That function call specifically calls a hypervisor. Okay? So you are going to do whatever you did in type 2 hypervisor. Type 2 hypervisor does this at runtime. Okay? In para-virtualization, you basically have the hypervisor is not scanning the code. Kernel programmer is scanning the code and said that's a sensitive instruction. It would never run inside a type 2 hypervisor. Let me go change it to a function. So you go and you modify the OS kernel, create a special version of the kernel that's specifically designed to run on a virtual machine. It wouldn't run on normal hardware because that function call is meaningless on normal hardware. You actually have to have the original sensitive instruction there. But this is a special variant that is designed specifically to run on a virtual machine. Okay? So essentially that's what is going to happen here. So if you have a type 1 hypervisor, you are going to make a trap. If you have para-virtualized OS, instead of running an unmodified OS, you are going to run what is called a para-virtualized OS, where you modified the OS. Essentially every time you want to execute this sensitive instruction, you have at coding time change that to a function call. You are just directly going to call the hypervisor and you will be done. Okay? So this is the only way to run a type 1 hypervisor on older hardware, okay, where you do not have this property. Okay? If you don't have this property, the only way you can make it work is modify the OS, take out every sensitive instruction and change it to a function call. So that when the OS executes, it directly calls the hypervisor saying, go do this, okay, which is the equivalent of what the sensitive instruction would have done. Okay. So if you have old versions of hardware, the only way to run type 1 hypervisor is to run a para-virtualized OS. It requires you to have access to the code of the OS. If you're buying a commercial OS like Windows, you cannot actually do this unless Microsoft has itself done it for you. Okay, but if you have Linux or any open source OS, you can go change the code yourself and implement a para-virtualized version of a kernel that then runs on a type 1 hypervisor. Okay. That's referred to as para-virtualization. Okay, so these function calls in a para-virtualization world are called hypercalls because they make a call to the hypervisor. In a normal OS, you have system calls. Processes call the OS or operating system using a system call. Here, the OS is calling the hypervisor using hypercall. So every sensitive instruction gets replaced by a hypercall. The hypercall is an interface that the type 1 hypervisor has exposed, okay, to a modified OS, and it implements those sensitive instructions on behalf of the OS. Okay, any questions? All right. So those are 3 types of hardware level virtualization. I think we are kind of out of time here. So I'm going to talk about how to virtualize CPU. Okay, I didn't talk about how to virtualize memory and how to virtualize the disk. I'm going to talk about that next time, and then we'll also talk about OS virtualization next time, a different technique. All right, so we'll stop here today, and then we'll continue next time.